Groundbreaking discovery. Aluminum-20, the new three-proton emitting isotope. Imagine a nucleus that defies the rules of stability. Just a single atom that breaks the natural balance of protons and neutrons. Scientists have just uncovered a fascinating new isotope, Aluminum-20, which doesn't just emit a proton, but three. This discovery challenges our understanding of nuclear physics and opens a door to exploring the extreme end of the atomic world. But here's where it gets controversial. How does such a fragile nucleus even exist? And why is its decay so rare? Let's dive into the science behind this breakthrough. Radioactive decay is a natural process where unstable atomic nuclei release energy by emitting particles or radiation. Studying these decays helps us decode the hidden structure of elements, especially those far from the Valley of Stability, a region on the nuclear chart where most stable elements reside. Exotic decay modes, like proton emission, act as powerful tools to probe the mysteries of nuclei that don't follow the usual rules. In a groundbreaking study published in Physical Review Letters, https://link.aps.org/doi/10.103/revlet.128.021, researchers have now observed a previously unknown isotope, Aluminum-20, which decays via an extremely rare process called three-proton emission. The team, led by Associate Prof. Xiaoji Jiadong from the Institute of Modern Physics IMP in China, used advanced techniques at the GSI Helmholtz Center in Germany to detect this elusive nucleus. By analyzing the angular correlations of decay products, they confirmed that Aluminum-20, the lightest aluminum isotope ever found, lies beyond the proton drip line, a boundary where nuclei can no longer hold onto protons without falling apart. This isomer has 7 fewer neutrons than the stable aluminum isotope, making it one of the most neutron-deficient atoms ever discovered. The decay process of Aluminum-20 is both surprising and complex. It first emits one proton to form magnesium-19, a radioactive intermediate state. This magnesium nucleus then undergoes simultaneous 2-proton emission, leaving behind a stable dorsal nucleus. What makes this discovery unique is that Aluminum-20 is the first known isotope to emit 3 protons in a single decay event, with its first stage dorsal nucleus being a 2-proton emitter. This chain of events reveals a hidden layer of nuclear behavior that scientists had only theorized about before. But here's where it gets controversial. The decay energy of Aluminum-20's ground state is much lower than predicted by isospin symmetry models. Isospin symmetry suggests that particles like protons and neutrons behave identically in certain conditions, but this finding hints at a possible breakdown of that symmetry in Aluminum-20 and its mirror isotope Neon-20. This could mean that the rules governing nuclear forces aren't as uniform as we once believed. How do we reconcile this with the long-standing assumption of isospin symmetry? That's a question worth pondering. To put this in perspective, over 3,300 nuclei have been identified, but only 300 are stable and naturally occurring. The rest are unstable and decay through various mechanisms, from alpha decay to electron capture. While common decay modes were understood by the mid-20th century, recent decades have revealed exotic behaviors like single-proton radioactivity discovered in the 1970s and 2-proton decay observed in the 21st century. Now, 3-proton emission has been confirmed, pushing the boundaries of what we know about nuclear structure. This collaborative effort, https://phys.org/collaborative effort, involved researchers from IMP, GSI, Fudan University, and over a dozen other institutions, showcasing the global nature of scientific discovery. The study's theoretical predictions align with experimental results, reinforcing the idea that nuclear physics is a dynamic field constantly evolving with new insights. So what does this mean for the future of nuclear research? If Aluminum-20's decay reveals asymmetries in isospin symmetry, it could challenge fundamental theories about the strong force. Yet, as scientists continue to explore the unstable frontier of the nuclear chart, each new discovery brings us closer to understanding the universe's most basic building blocks. After all, the more we learn about the tiny particles that make up matter, the more we uncover the secrets of the cosmos. What will be the next big breakthrough? Let's keep the conversation going in the comments. What do you think about this radical new finding? Breakthrough. Aluminum-20 isotope discovered with rare 3-proton decay. Prepare to be amazed. Scientists have just identified a brand new form of aluminum that few people ever expected to see. This rare discovery, called Aluminum-20, offers deeper insights into the intriguing world of radioactive decay and the broader field of nuclear physics. But here's where it gets controversial. Some experts are debating whether this discovery confirms existing theories or signals we need to rethink our assumptions about how these nuclei behave. Most people know that elements have different forms, called isotopes, based on their number of neutrons. Of the more than 3,300 nuclides identified so far, less than 300 is stable and naturally occurring. The others are radioactive, meaning they progressively transform into different isotopes by emitting radiation. Common types of radiation like alpha, QH decay, beta decay, gamma radiation, and even fission have been known since the mid-20th century, but newer experimental achievements have revealed far more peculiar decay modes, especially in very neutron-deficient isotopes. In the 1970s, scientists first confirmed single proton radioactivity. Certain nuclei could shed a single proton as they decayed. By the 21st century, researchers found heavier nuclei that emit 2 protons at once. More recently, investigators have even observed extremely rare cases involving 3, 4, or even 5 proton emissions during these fleeting decay processes. Enter Aluminum-20, highlighted by physicist Dr. Yaodong Xu from the Institute of Modern Physics at the Chinese Academy of Sciences. According to Dr. Xu, Aluminum-20 is the lightest aluminum isotope that has been discovered so far, located well beyond the proton drip line, meaning it has far fewer neutrons, 7 fewer in fact, than the common and stable aluminum you might find in everyday objects. For this study, the research team employed what's known as an in-flight decay method at the fragment separator of the GSI Helmholtz Center for Heavy Ion Research. After producing Aluminum-20, they tracked the emission of its decay products by measuring their angular correlations. Through detailed analysis, the scientists found that Aluminum-20 first decays by emitting a single proton to form magnesium-19. Then, magnesium-19 itself undergoes a nearly simultaneous 2-proton emission. This series of events amounts to a 3-proton release overall, making the Aluminum-20 the first known 3-proton emitter, whose 1-proton emission daughter nucleus, magnesium-19, is also 2-proton radioactive. And this is the part most people miss. The decay energy of Aluminum-20 is quite a bit lower than what you'd expect from standard isospin symmetry predictions, hinting at possible isospin symmetry breaking. Essentially, Neon-20, often regarded as the mirror partner to Aluminum-20, appears to behave differently in terms of nuclear spin and parity. Theoretical calculations back up the notion that Aluminum-20's ground state spin parity doesn't match that of its Neon-20 counterpart. Could this be a fundamental challenge to nuclear physics as we know it? We believe our findings open up exciting new chapters in understanding how proton emission works. Dr. Xu emphasized. They also shed light on what can happen to nuclei once they cross that proton drip line, where the balance of protons and neutrons becomes extremely delicate. Beyond basic science, these results encourage deeper reflection on whether similar decay processes might be lurking in other isotopes that have not yet been studied. The complete study is available in physical review letters. Doi 10.11.0.3, Dr. Physrevlet, Dr. Xu, Physrevlet.135.031. For further details on the future of isospin symmetry research, see the paper by XD Xu et al. 2025. Isospin symmetry breaking disclosed in the decay of 3-proton emitter 20L. What do you think? Does this surprising outcome confirm what we already know, or is it the first step toward upending certain assumptions in nuclear theory? Are we on the brink of discovering even more exotic isotopes with even stranger decay modes? Share your thoughts, question the data, or propose alternative explanations in the comments. After all, the more perspectives we gather, the closer we get to unraveling the mysteries at the heart of matter. Discovering Aluminum-20, the revolutionary 3-proton emitter. Imagine a groundbreaking discovery that challenges everything we thought we knew about nuclear physics. This is precisely what researchers have achieved with Aluminum-20, an isotope that defies conventional nuclear decay norms by exhibiting an extraordinary triple proton breakup. Radioactive decay is a natural phenomenon where unstable atomic nuclei release energy in the form of radiation. Understanding the various modes of nuclear decay is essential for gaining insights into the characteristics of atomic nuclei. Among these, exotic decay modes, such as proton emission, serve as vital tools for exploring the structure of nuclei that lie far from the stability region, essentially the area on the nuclear chart where stable nuclei reside. In a remarkable study published in the esteemed journal Physical Review Letters on July 10th, a team of physicists with the Institute of Modern Physics IMP at the Chinese Academy of Sciences, CAS, along with their collaborators, unveiled the first observation and detailed spectroscopy of Aluminum-20. This isotope, previously unknown and unstable, undergoes the rare process of emitting 3 protons during its decay. Aluminum-20 is the lightest isotope of aluminium that has been identified to date. It exists beyond the proton drift line and contains 7 fewer neutrons than its stable counterpart, explained Associate Professor Xiaodong Zhu from IMP, who is the lead author of the study. Utilizing an innovative in-flight decay technique at the fragment separator located at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany, the researchers meticulously measured the angular correlations of the decay products from Aluminum-20. This led to the discovery of the previously uncharted nucleus Aluminum-20. Through a comprehensive analysis of these angular correlations, the team determined that the ground state of Aluminum-20 first decays by emitting a single proton, transitioning to the intermediate ground state of Magnesium-19. This is then followed by the decay of Magnesium-19, which emits 2 protons simultaneously. Notably, Aluminum-20 is the first 3-proton emitter observed where the daughter nucleus from its 1-proton decay is itself a nucleus that undergoes 2-proton radioactivity. Additionally, the researchers found that the decay energy of Aluminum-20's ground state is significantly lower than what would be expected based on isospin symmetry predictions. This discrepancy suggests a potential breaking of isospin symmetry in Aluminum-20 and its mirror isotope Neon-20. The findings are further corroborated by advanced theoretical calculations, which indicate that the spin parity of Aluminum-20's ground state differs from that of Neon-20's ground state. This research enhances our comprehension of proton emission phenomena and sheds light on the structure and decay processes of nuclei that exist beyond the proton drift line, stated Zhu. To date, scientists have catalogued over 3,300 nuclides, yet fewer than 300 of these are stable and can be found in nature. The rest are unstable and undergo radioactive decay. By the mid-20th century, several common decay modes had been identified, including alpha decay, beta-minus decay, beta-plus decay, electron capture, gamma radiation, and fission. In recent decades, advancements in nuclear physics, experimental facilities, and detection technologies have enabled scientists to uncover various exotic decay modes, particularly in neutron-deficient nuclei. In the 1970s, the phenomenon of single proton radioactivity was discovered, when nuclei decay by emitting a single proton. As we entered the 21st century, 2-proton radioactivity was identified in certain extremely neutron-deficient nuclei. More recently, even rarer decay events, such as 3, 4, and 5-proton emissions, have been observed. This significant collaborative research effort involved contributions from IMP, GSI, Fudan University, and numerous other institutions, showcasing the power of teamwork in scientific discovery. The work received support from various funding sources, including the National Key R&D Program of China, the CAS President's International Fellowship Initiative, and the National Natural Science Foundation of China, among others. But here's where it gets controversial. What does this mean for our understanding of nuclear stability? Could there be more undiscovered isotopes that challenge our current theories? We invite you to share your thoughts and opinions in the comments below. Do you agree with the implications of this research, or do you see it differently?